colloquium today. So Anna is my first student defending her thesis here, so I think I'm equally excited. I think excited is the right word, as Anna is over this experience. But I'm not the only one who has been guiding Anna through this process. Anna did the first half of her thesis under the guidance of Ruth Clay this year, so we're very happy that he can join us. But 2 years ago, Anna decided to join the astrochemistry group. And Anna, as you will see, is a theorist, and I am most definitely not. It was a brave decision on her part. But I think it's been a wonderful adventure together, and it's definitely been a great learning experience for me to have to delve into some of the physics that is underpinning the assumptions we make on the chemistry as planets are forming. So I'm looking forward to another great learning experience today. So Anna, please go ahead.
So thank you, Karin, and thank all of you for being here today, I guess for the third or fourth thesis presentation in a week. So before I go into the science part of my thesis, I have to tell you that for me this PhD has really been a rocky road, as I think is the case for many of us here. And so there are many people that I would like to thank for not only making this possible, but also making it enjoyable, at least at most times. So first of all, I would like to thank Karin. Karin was my mentor for a year, and then my thesis advisor for the last 2 years. And none of this would have been possible without her constant encouragement, advice, support, feedback, and so on. She has helped me become a better scientist and a more independent one. And I would not be standing here today talking to you about my thesis if it wasn't in a large part due to Karin. So thank you, Karin. I would next like to acknowledge Ruth, who's my advisor for the first 3 years, and who has guided me towards my first steps into doing real astronomy research when I really had no idea what I was doing, at least at the beginning. And she's helped me and always encouraged me to be confident and independent. And I'll remember fondly the many hours that we spent doing order of magnitude calculations in her office or group meetings or in class and so on. So thank you, Ruth. I'd like to give a special thanks to Roseanne, who was my faculty mentor for last 2 years. And I've benefited tremendously from all her support and advice, both in professional and personal issues. And I think that our almost weekly breakfasts at Sarah's or Hira's were definitely the highlights of most of my Thursdays. Thank you. I want to thank my collaborators, Teal, Jamila, and Andrew. This thesis was possible largely due to their collaboration, and I've generally enjoyed working with them and learning from them. Of course, I want to thank my thesis committee, Dimitar, Matt, Sean, and especially Fred, who came here all the way from Chicago. They have helped me put me on this, guide me towards the right steps to completing this thesis, and I hope to be even more thankful to them a few hours from now. I would really like to thank the astrochemistry and disc groups here. As the name goes on 4 lines, I'm not going to read them all, but I just want to say that I've learned a lot from them, and they've also helped me a lot with very useful suggestions and feedback on my research. And to thank Courtney and Meredith, whose name is already up there, for putting up with me as their office mate for 4 and 1 year, respectively, as well as Beck and Anjali, who are my group mates for 3 years, and with whom I spend many hours and days at conferences and workshops and practice talks and whatnot. And to thank Peg and Rob, who run this department so smoothly and who always do it with a smile on their faces, be it when I bump into them in their corridor or when I barge into their office asking for one thing or another. And of course, I want to thank all the graduate students in the department. A large reason why this PhD was enjoyable was thanks to you guys. So I really want to thank everyone who's in the room or who's not in the room. Thank you. This would not be complete if I didn't acknowledge my friends outside of astronomy, who have supported me either from here in Boston or from New Jersey, from California, or from all the way back home in Romania. And from going out for frozen yogurt to late movie nights to just taking me out for a beer, they've constantly reminded me that, at least occasionally, I can actually have a life outside of astronomy as well. And finally, but perhaps most importantly, I want to thank my family for loving and supporting me for the last 30 years, the past 10 of which was from really far away. And unfortunately, my parents couldn't be here today because of the faraway thing, but they're keeping their fingers crossed for me and waiting for good news later today. So I hope I can deliver. So that being said, for the past 4 years and a half, I've been particularly interested in 2 fundamental questions in planet formation theory. The first question is, where in the disk can giant planets form? So how does the dislocation and properties regulate the formation of giant planets. The second question is what compositions will the formed giant planets have obtained? How does the composition of the disk relate to the eventual compositions of mature planets? So, in the last 2 decades or so, there's been more than 2,000 exoplanets that have been discovered. And as you can see in this plot, there's a very large variety in terms of their masses and semimajor axes. For the purpose of my thesis, I'm primarily interested in gas giants. And as you can see here, gas giants have been detected at a very wide range of orbital separations. And so gas giants are very important and very interesting because gas giants shape the orbital architecture of the planetary system they're in, and they affect the delivery of volatile materials to terrestrial planets. Gas giants are also much easier to observe just because they're so much bigger than lower mass planets. So they're easier to find, and it's also easier to detect their atmospheric spectra, from which you can obtain some information about their chemical compositions. At the same time, gas giants are also more difficult to form because there needs to be enough gas in the disk for them to become this puffy big gas giants. And they also need to be able to accumulate this disk material before it dissipates from the disk, which happens in relatively short timescales. So, since we know that planets form in disks, this means that the composition of planets is determined by and is very tightly linked to the composition of the disk in which they are born. And so, if we want to understand more about planets, we first need to better understand the disk in terms of its structure, composition, evolution. And so, in my thesis, I approached this very tight link between disks and planets from 2 directions. In the first part of my thesis, I investigate the role of dislocation in the formation of wide separation gas giants. Well, in the second part, I look at the effect of disk structure and composition at different radii on the eventual composition of giant planets. So let's talk about the first part, and specifically about minimum core masses for giant planet formation. So when we think of minimum core masses, we think of core accretion. And in the core accretion model, in order to form a giant planet, you first need to form a solid core. This core grows, and once it becomes massive enough, it can accumulate a significant atmosphere. So how big of a core do you need? The typically quoted value is around 10 Earth masses. But this is not a constant, and it depends on disk properties and on how fast the core grows. We know from observations that protoplanetary disks dissipate on relatively short timescales of a few million years, which means that cores must grow fast in order to form gas giants. And this is particularly challenging in the outer disk, where dynamical times are long. At the same time, however, we have seen in recent years giant planets that have been directly imaged at wide separations, such as the HR 8799 system here. And this poses an intriguing question. How did these planets form? So this is what I investigate in this part of my thesis. And specifically, I answer the following question. What is the lowest possible core mass required to form a gas giant before disk dissipation? Now, as I said earlier, in order to form giant planets, cores have to grow fast, which means that on average, they need high planetesimal accretion rates. So let me first talk about studies that consider these high rates. So in these studies, the incoming planetesimals heat up the core's atmosphere, which in exchange releases energy, resulting in high luminosity. So in this scenario, the atmosphere is in steady state at all times, where all the energy due to planetesimals is radiated away by the atmosphere. So the core and the atmosphere grow simultaneously, and the mass of the atmosphere is a function of the mass of the core. So let's look at this more closely. Since the mass of the atmosphere is a function of the core mass, for a given set of disk conditions and a prescribed planetesimal accretion rate, every core mass maps uniquely to one atmosphere mass. So the core and the atmosphere grow together, and at some point, their masses become comparable. At this stage, a rapid phase of runaway gas accretion starts, and a big, puffy gas giant is formed. So in this scenario, again, for a set of disk conditions and a prescribed accretion rate, there is a uniquely determined core mass for which the mass of the atmosphere is equal to the mass of the core. And this is what these studies call the critical core mass. This is the minimum core mass required to form a gas giant. Now, high planetesimal accretion rates mean that cores can grow quickly. But this poses an additional challenge. because fast accretion heats up a core's atmosphere, inhibits the ability of the atmosphere to cool and contract, and therefore it eventually increases the critical core mass. And again, this is problematic for the outer disk, where it's hard to form large cores on relatively short timescales. In fact, a study from 2011 by Roman Rafikov has shown that core accretion cannot operate beyond 40 to 50 AU at the accretion rates that are required to form the core and the atmosphere on the same timescale. But this is not all bad news, and maybe we can look at this problem from a different angle. And this is what I do in this part of my thesis. And the first thing to consider is that planetesimal accretion does not need to be constant at a given location in the disk throughout the disk lifetime. And there are several studies and simulations that have shown that this is a viable scenario. So let's imagine it. We have a core. It's being bombarded by planetesimals. It's growing fast, but the atmosphere stays small by comparison. And at some point, planetesimal accretion goes down. So now the core no longer grows significantly, and the energy due to planetesimals can no longer balance radiative losses by the atmosphere. So now the envelope accretes gas while undergoing Kelvin-Helmholtz contraction. So in this scenario of low planetesimal accretion, the atmospheric evolution is dominated by Kelvin-Helmholtz contraction. Now, remember that I told you that in cases that consider high planetesimal accretion rates, the atmosphere is in steady state, and the mass of the atmosphere is a function of the mass of the core. In this complementary regime that we consider, where KH contraction dominates atmospheric evolution, the mass of the atmosphere is a function of time. And so we have a core of fixed mass that is slowly accumulating an atmosphere up until the core and the atmosphere have comparable masses, which is when runaway gas accretion starts. So in this scenario, any core can, in theory, have an atmosphere with a mass equal to its own. But of course, the question is, how fast can this atmosphere form? And at the very least, it needs to grow before the gas in the protoplanetary disk dissipates. So what we call the critical core mass in this regime is the core mass that can accrete an atmosphere with a mass equal to its own on a timescale that is equal to the disk lifetime. And I want to emphasize that this is a minimum critical core mass, since, as I said earlier, any additional heating due to planetesimals would inhibit the ability of the atmosphere to cool and would increase this critical core mass. So this was my goal in this study. I determined the minimum critical core mass required to form a gas giant before disk dissipation, assuming that planetesimal accretion is low and the atmospheric evolution is dominated by Kelvin-Helmholtz contraction. Moreover, since I wanted to obtain robust quantitative results for this critical core mass, I calculated it using a realistic equation of state for the nebular gas and realistic dust opacities. So let me briefly summarize the assumptions of one model. Since we're in a low planetesimal accretion regime, the core no longer grows and has a fixed mass. The planet is embedded in the gas disk, and the atmosphere is spherically symmetric and in hydrostatic balance. We consider a two-layer atmosphere composed of an inner convective region and an outer radiative region. One additional assumption that we make is that the luminosity is constant throughout the outer radiative layer of the atmosphere. And this proves to be a good approximation for most of the cases that we're interested in, with one exception that I will talk about later. And so we use the standard equations of stellar structure to create a series of static atmospheric profiles that we then connect temporally through a cooling equation of the form L equals minus dE dt. So here, I'm just showing an example of our results. On the left, it's a radial pressure profile. R is the atmospheric radius. And on the right is the time evolution as a function of total mass, core plus atmosphere. So the only reason I'm showing you these plots is just to give you a visual idea of how results look like. What I do want to emphasize is that the atmospheric profile is determined by the adiabatic gradient del ad defined here. Because the adiabatic gradient relates to gas pressure, temperature, and density, and therefore it can be used to parameterize the equation of state. This is very important, and it leads me to the next thing that I want to talk about, which is the fact that the atmospheric evolution, and therefore the critical core mass, are highly dependent on the gas equation of state and on the dust opacity. So let's explore each of these effects separately, and let's start with the equation of state. And since for now I'm just focusing on the EOS, I'm going to assume that the opacity is the standard ISM opacity. So the equation of state can be parameterized by the adiabatic gradient. For an ideal gas, delta is constant, but for a realistic EOS, delta is variable. So these are contour plots of the adiabatic gradient as a function of gas temperature and pressure for a realistic EOS. The upper right rectangles are the original Samon et al. Equation of state tables, while the rest of the plot is our extension to lower temperatures and pressures. So at high temperatures, molecular hydrogen dissociates, and at even higher temperatures, atomic hydrogen ionizes. Both of these processes require energy, which explains the features that we see in the adiabatic gradient in dissociation and ionization regions. So what happens at low temperatures? Well, at low temperatures, the rotational states of the hydrogen molecule are only partially excited, so it no longer behaves like an ideal gas. And the reason for that is that molecular hydrogen comes in two spin isomeric forms. There's orthohydrogen with parallel proton spins and parahydrogen with anti-parallel proton spins. And these two spin isomers can either be in thermal equilibrium, as shown on the left, or in a fixed 3-to-1 ratio, which is the ratio they reach at room temperature, as shown on the right. Now, thermal equilibrium between ortho and parahydrogen means that there has to be some interconversion between the two spin isomers, which again requires energy. So again, this explains why there's a feature in the adiabatic gradient for the equilibrium case, and why that feature does not exist for the fixed ratio case. For the parameter space that we're interested in, we have found that ortho-para equilibrium is achievable during the disk lifetime. So this is what we assume as our fiducial model. Okay, so how do all these features in the adiabatic gradient affect the atmospheric evolution and the critical core mass? Turns out that these variations in delta, due to non-ideal EOS effects, increase the critical core mass compared to an ideal gas. So here, I'm showing you critical core mass as a function of semimajor axis for a typical disk lifetime of 3 million years. So this is a result for an ideal gas, the realistic EOS with the spin isomers in equilibrium, and the realistic EOS with a fixed 3-to-1 ratio. So the first thing to notice is that the critical core mass decreases with semimajor axis. And this is because lower disk temperatures give lower critical core masses. So you can see that the realistic EOS with the equilibrium case increases the critical core mass by about a factor of 2 compared to the ideal gas. And this increase is even larger for the fixed ratio case. So if we look at the numbers on the blue curve, they're pretty large. They're overall larger than internet masses that I quoted at the beginning. But this is not the end of the story, and leads me to the next thing that I want to talk about, which is the effect of dust opacity on atmospheric evolution. It's a well-established fact that lower opacities accelerate atmospheric growth and therefore decrease the critical core mass. So we have used realistic opacity tables that take into account gray growth to calculate accrete. And these opacity models assume a power law distribution for the particle size. In this case, the power law coefficient is 3.5, which corresponds to a standard collisional cascade, and the maximum particle size is 1 centimeter. So here, I'm showing you the critical core mass for the realistic EOS and both the ISM and grain growth opacities. So the first thing we notice is that grain growth dramatically decreases the critical core mass. And this is what we expected, since, as I said earlier, lower opacities are going to give lower critical core masses. The other feature that we notice is that grain growth makes the critical core mass much flatter with semimajor axis. And this is because grain growth opacities are much less sensitive to changes in temperature, and therefore to the disk location. So if you want some numbers to take home, here it is. For a realistic EOS and grain growth opacity, the critical core mass is about 8 Earth masses at 5 AU, decreasing to 5 Earth masses at 100 AU. So now, this number looks nice. They're lower than 10 Earth masses, even in the more inner parts of the disk. And it turns out that we can get even significantly lower than that if we take into account grain coagulation, which can be approximated by a power law coefficient of 2.5 in the particle size distribution. Our model is not equipped to calculate the critical core mass for grain growth with coagulation, because the core masses become so low that the radiative layer of the atmosphere becomes very large. So our assumption of constant luminosity in this region breaks down. So while we cannot calculate accrete for grain growth with coagulation, based on our calculations for the runaway accretion time of the atmosphere for both grain growth with and without coagulation, we can claim that grain coagulation may actually decrease the critical core mass by an order of magnitude. So mcrete may be as low as 1 Earth mass. And so the point that I'd like you to take away from this part of my talk is that the minimum critical core mass to form a gas giant depends highly on disk location and properties and may be as low as 1 Earth mass. So I think this study clearly challenges previous claims that core accretion cannot operate in the outer disk, and therefore it reopens the case for in situ formation of wide separation gas giants. Okay, so I'm going to bring this cartoon back just to remind you there's a very tight link between disks and planets, and that disk compositions regulate planet compositions. So let's move on to the second part of my talk and talk about the effect of disk structure and composition on the composition of gas giants. So, and more specifically, let's talk about snowline locations in disks and the carbon over nitrogen over oxygen ratios. So, the basic overarching idea of this part of my thesis and beyond is that I want to understand the disk well enough to, first of all, predict what are the kinds of planet compositions that result from planet formation in different parts of the disk, and conversely, backtrack the planet formation location based on the planet composition. These are really complicated. This is a very nice cartoon showing several chemical and dynamical processes that occur in disks. For the purpose of my thesis, I'm primarily interested in processes that occur in the disk midplane, since that's where planets form. And specifically, I've investigated dynamical processes such as transport of both gas and dust, as well as different ice morphologies. And so, while disks are complex, we do know some things about them. In particular, we know that snowlines of volatile molecules have been detected in disks. And this is very important because it gives us some information about the chemical composition of the disk in gas and in dust at different radii, which has direct implications for the composition of giant planets forming in these locations, both for the molecular compositions as well as for the elemental compositions and elemental ratios. So this is a detection of the CO snowline in TW Hydra, a 30 AU. And the reason there's an N2H plus plot here is because N2H plus is a very good tracer of CO, since it becomes very abundant as CO is destroyed. So now, this is just one example of a snowline detection, but other snowlines have been observed. The water snowline has been detected also in TW Hydra, and there's also an observation, a detection of another CO snowline in HD 163296. And aside from water and CO snowlines, there are several other important snowlines in disks created by the major carbon, oxygen, and nitrogen carriers. So here, I just want to show you an example of how they look. So what I'm showing here on the y-axis is the total elemental abundance of carbon plus nitrogen plus oxygen in grains, so in solids, as a function of semimajor axis. So here you can see the water, ammonia, CO2, methane, CO, and N2 snowlines. And you can see that at each of these snowlines, the total elemental abundance changes. So this supports the point that I made earlier, that these snowlines are going to modify the elemental abundances both in disks and in giant planet atmospheres, as well as the elemental ratios. And one elemental ratios that people have been particularly interested in is the carbon to oxygen, or C2O ratio. So the C2O ratio is an important signature of atmospheric chemistry. This is a theoretical model which shows that by varying the C2O ratio by a factor of 3 in an exoplanet atmosphere, changes the abundance of other volatiles, such as water or methane, by several orders of magnitude. So clearly we need to look at this C2O ratio more closely. A few years ago, there were some claims that some giant planets may have C2O ratios that are larger than the stellar value, such as WASP-12b. These claims have since been unequivocally refuted. However, in the near future, hopefully, with JWST, we're going to be able to obtain many more atmospheric spectra and be able to better constrain atmospheric compositions, and therefore the C2O ratio. And also from a theoretical standpoint, it's still interesting to consider why the C2O ratio in a disk or in a planet atmosphere would be different from the stellar value. And a possible explanation is that the main carrier of carbon and oxygen, which are water, CO2, and CO, have different condensation temperatures. And so there will be variations in abundances of these volatiles, on the abundances of carbon and oxygen in solids and in gas, between the snowlines of these volatiles, which is going to change the C2O ratio throughout the disk. And this is an idea that Karin, Ruth, and Ted Bergen came with a few years ago. This is a plot from their paper showing the C2O ratio in gas and in dust as a function of semimajor axis. And here are the water, CO2, and CO snowlines. So you can see that you can indeed obtain a superstellar C2O ratio in gas, particularly in the outer disk between the CO2 and CO snowlines, where oxygen gas is more depleted. And in this region, the C2O ratio reaches unity, and so it's enhanced by a factor of 2 compared to the stellar value. So Karin's model was great, and it was the starting point of this part of my thesis. But Karin's model assumes a static disk, which is purely irradiated by the central star, does not experience any redistribution of solids, any gas movement, and the chemistry is static. So basically, everything just stays as it is. But in reality, as I showed earlier, there are many chemical and dynamical processes that occur in disks, which are going to change the abundances of these volatiles, their snowline locations, and therefore the C2O ratio. And so, in this part of my thesis, I'm looking at two particular dynamical processes, which are radial drift of solids and viscous gas accretion into the central star, as well as the different ice morphologies, and investigate how they affect the snowline locations of the main carbon and oxygen carriers, as well as and therefore the C2O ratio in gas and in dust throughout the disk. So, just as a brief reminder on radial drift, we know that solids in a disk, they move around the star on their Keplerian orbit. The gas, however, experiences an extra pressure gradient, which makes it move slightly slower at a sub-Keplerian velocity, which can be approximated by this formula here, where Cs is the sound speed. So small particles, micron size, they're well coupled to the gas, so they move with the gas on the sub-Keplerian orbit. At the opposite end, large particles, kilometer-sized and above, they don't care about a gas drag, so they just stay on their Keplerian orbits. But then there's a range of intermediate-sized particles, and I put this in quotation mark because it really depends on disk properties and dislocation, though they're usually in the centimeter to meter size range. These particles experience a headwind due to gas drag. They lose angular momentum, and therefore they drift towards the central star, which we know as the meter-size barrier. The meter-size barrier is not the scope of my research, but what I want to point out is that drift may be important in determining the locations in the disk where particles of different sizes desorb, and therefore where snowlines are located. In addition to that, we know that the gas disk viscously accretes onto the central star. And for this, we use the standard alpha disk prescription, where the kinematic viscosity is given by a dimensional coefficient alpha times the sound speed times the disk scale height. So here I'm showing you an example of the gas surface density as a function of a normalized radius at several stages in the disk evolution. And this is a self-similar solution for a gas surface density, where sigma is a power law in radius with an exponential cutoff at a specific radius. And the reason I'm showing this particular example is that we also use a self-similar solution for the surface density in our active disk model. So now, before you look at this plot, I want to point out that if you want to understand where the drift and accretion affect desorption, as a first order of magnitude calculation, we need to compare the timescales for these processes. So here, I'm showing you time as a function of particle size. So the solid lines are the drift timescales, calculated at 3 locations, as I'll explain in a minute. The dashed lines are the desorption timescales, calculated at the same locations. And the dotted lines are the gas accretion timescales. And finally, the black dashed dotted line is this lifetime of 3 million years. And before I go into more details, I want to point out that these are order of magnitude estimates. So these are not numbers to take home. And so we perform these estimates at the water, CO2, and CO snowlines in a static disk, it's like the one from Karin's model, since those are the regions in the disk where desorption is going to happen. So these locations are representative. And so I'm not going to go into the details of this plot. But what I want to point out is that there's a region here. There's a range of particle sizes for which all these timescales are comparable. And so the simple estimate tells us that we do have to take into account radial drift and gas accretion when we calculate the distance at which particles of different sizes desorb. And so with that information in mind, we went ahead and did the actual calculation. And what we have found is that there is indeed a range of particle sizes that desorb at a fixed location in the disk that only depends on the particle size, regardless of their initial position in the disk. And for particles in the size range, this desorption happens really quickly. So a particle drifts, and it desorbs really fast, very short time scale, and in a very narrow distance range. So what this tells us is that for particles with sizes in this range, there's a fixed, sharp snowline location that only depends on the particle size. So with that information, we can go ahead and calculate these snowline locations and make some estimates for the C2O ratio. So here, I'm showing you the C2O ratio as a function of semimajor axis for this range of particle sizes that, as I said, desorb at a fixed location in the disk and that form fixed sharp snowlines. So it's the C2O in gas, in dust, and then the black lines are the C2O ratios for a static disk for comparison. So this is the range of water, CO2, and CO snowlines. And we made this calculation for 3 disk models, as I'll explain in a second. So the first thing that I want to point out is that the snowlines move inward as the particle size increases. And we know that realistic particle size distributions are dominated in mass by the largest particles. And so what this tells us is that if we have a particle size distribution and a maximum particle size, we can go ahead and pick the appropriate snowline from one of these plots. So now, the top panel is our result for an irradiated disk, which, as the name suggests, is purely irradiated by the central star, does experience radial drift, but there's no gas movement. And as I said earlier, small particles are well coupled to the gas. And the gas here is not moving. So it's only particles about 0.5 centimeters and above in our model that decouple from the gas, drift, desorb, and form snowlines, as shown here. The middle panel is our result for an evolving disk, which is an active disk in which we took into account the radial movement of the gas, but we still assume the temperature profile of an irradiated disk. So now, small particles are still well coupled to the gas, but now the gas is moving and is dragging them with it. So now, millimeter-sized particles and lower are going to form snowlines as well, which explains these additional lines here. And finally, the bottom panel is our result for a viscous disk, which is an active disk in which we also include accretion heating, since both stellar irradiation and accretion heating contribute to the thermal evolution of the disk. So if you compare the CO2 and CO snowlines between these two plots, there's really no difference. And this is because past a FIAU, stellar irradiation dominates. What does change is the location of the water snowline, which is significantly pushed outward. And this is because accretion heating dominates in the inner disk, temperatures are higher, and therefore water particles are going to desorb larger distances. Now, I should explain the arrows on these plots. So when we calculated the C2O ratios in active disks, so where the gas is flowing, we did not account for the fact that the desorbed icy particles and the overall nebular gas may have different fluxes. So for example, an icy particle that crosses the water snowline desorbs if its flux inside a water snowline is larger than the overall flux of the nebular gas. This is going to cause an excess of oxygen gas inside a water snowline, which is going to decrease the gas phase C2O ratio in this region. These arrows are by no means quantitative, but this decrease can actually be substantial. So we found that for the largest drifting particles in our model, which are about 7 meters, the flux of the desorbed icy particles inside a water snowline is about 1,000 times larger than the flux of the overall nebular gas. So this can be a substantial decrease. And the same holds true inside a CO2 snowline, while there will also be an excess of oxygen gas due to CO2 desorption. So finally, perhaps the most interesting feature of these plots, at least to me, is that if you compare the black lines with the static snowlines, and with the innermost snowlines that can be created by drift and accretion, so the red ones, there's a pretty big difference. So it turns out that radial drift and viscous gas accretion may move the water, CO2, and CO snowlines inward by about a factor of 2 compared to a static disk. So I think it's very nice that from such a simple semi-analytical model, you obtained such a strong result that has direct implications for the compositions of giant planets forming in this disk. At the same time, this has also told us that radial drift and gas accretion introduce some uncertainty in the locations of these snowlines. But this is not the end. Because aside from these dynamical processes, ices can also have different morphologies. So they can be pure ices, mostly pure ices, or they can be layered on a water ice substrate. And since water is the least volatile species that is very abundant in disks, its binding energy is larger than that of other volatile species. And so if an ice is in a water-dominated environment, its binding energy is going to be larger than if it's a pure ice. And this is particularly important for CO because its binding energy is so different from that of water. And to quantify that, we used results from laboratory experiments performed here by Edith Fayol. So here I'm showing the results of a temperature-programmed desorption experiment that shows the desorption rate as a function of temperature. Here is for CO as pure ice and CO on water ice. And you can see that the peak of the desorption curve, which is correlated to the binding energy of CO, it has a significantly higher temperature when CO is in a water-dominated environment. And it turns out that the binding energies of CO may vary by a factor of 1.7 up to a factor of 2, depending on its binding environment. And this is important because this is going to change the location of the CO snowline. So by how much? So I'm going to show a plot that's very similar to the one that was 2 slides ago. So this is again the C2O ratio as a function of semimajor axis. The top plot is a result for pure ice, so identical to the one from the previous plots. And then here is the result for CO in a water-dominated environment. And we made these calculations for the viscous disk, since that's the most realistic disk from all our 3 disk models. So I've already shown, these are the water, CO2, and CO snowlines. And I've already shown that this dynamics moves not only the CO snowline, but also the water and CO2 snowlines by about a factor of 2. It turns out that ice morphology can have an even larger effect. So depending on the particle sizes, the snowlines may move inward, the CO snowlines may move inward by factors of 3 to 4. So if we take these 2 effects together, it turns out that this dynamics and ice morphology may change the location of the CO snowline by a factor of 7. So in our case, the CO snowlines may span anywhere between 9 and 61 AU, which is a huge range. And this is going to cause a large uncertainty in the locations in the disk where the C2O ratio in gas is enhanced. So what this tells us is that we need more information. We need additional species and additional elemental ratios if we want to better be able to constrain the composition of disks and planet atmospheres. So one thing we can do is to look at nitrogen and nitrogen carriers. So nitrogen is important. It's abundant in the solar system, and it's primarily found as N2. We cannot detect N2 directly, but we can detect other nitrogen carriers. So here I'm just showing an example of several nitrogen carriers and their abundance in comets. And you can see that ammonia is the most abundant observed nitrogen carrier. However, the ammonia abundance is only a small fraction of the total elemental nitrogen abundance in the solar system. And this is what tells us that most of the nitrogen is in N2. And since N2 is very volatile, then we expect wide separation gas giants to have an excess of nitrogen in their atmospheres, which may be used to trace their formation origins. So we considered N2, and even though the ammonia abundance is small compared to that of N2, we still consider ammonia as well. And to explore the range of possible ammonia abundances, we use the median and maximum ammonia abundances observed towards protostellar core from the Spitzer C2D legacy ice survey. So basically we add N2 and ammonia into our model and calculate N2O ratios. But before I go to the results for that, I just want to quickly discuss the binding behavior of N2. So here on this plot, I've added the N2 desorption curves, and you can see it has a very similar behavior to that of CO. So the peak of the desorption curve, it's also at a higher temperature when N2 is in a water-dominated environment. And the binding energy of N2 also varies by about a factor of 7, depending on its binding environment. Okay, so now let's look at N2O ratios. Let's start with a static disk, like in Karin's model. So here, I'm showing the N2O ratio, gas and in dust, is a function of semimajor axis. The top panel is assuming that all nitrogen is N2, so there's no ammonia. The middle panel assumes the median observed ammonia abundance in protostellar cores. And the bottom panel is the maximum observed ammonia abundance. And we made this calculation for CO and N2 as pure ices. So there are a couple of things to notice. First thing is that if we look at the bottom plot, you see that even the maximum abundance of ammonia does make a moderate difference in the N2O ratio between the ammonia and CO2 snowlines. But it's not a large difference, especially given the other uncertainties that come into calculating N2O ratios. What I think is more interesting is that if you look at the top plot, you see that the N2O ratio in gas is highly enhanced compared to the stellar value throughout most of the disk. So remember that I told you that in the case of the C2O ratio, the gas phase C2O ratio was enhanced by a factor of 2 between the CO2 and CO snowlines. The N2O ratio, on the other hand, is already enhanced by a factor of 2 outside the water snowline, by a factor of 3 between the CO2 and CO snowlines, and by many, many orders of magnitude between the CO and N2 snowlines, where oxygen gas is depleted. So given this very high enhancement of the N2O ratio, this tells us that we may use N2O ratios, in addition to C2O ratios, to better constrain disk and planetary atmosphere compositions. So this is a story for a static disk. How does it look for a dynamic disk? So here, I'm showing, again, a very similar plot to previous plots. But now this is the N2O ratio, not the C2O, as a function of semimajor axis. So these are the water, CO2, CO, and N2 snowlines. The top panel is for CO and N2 as pure ices, and the bottom panel is for CO and N2 in a water-dominated environment. And the effect on the snowline location of disk dynamics and ice morphology is very similar, both qualitatively and quantitatively, as in the case of CO. So disk dynamics and ice morphology also may change the location of the N2 snowline by a factor of 7. So in our model, the N2 snowlines may span anywhere between 11 and 79 AU. So again, there's also very large uncertainty in the location of the N2 snowlines, and therefore in the regions of the disk that have high, very enhanced gas phase N2O ratios. And so there are 2 points that I'd like you to take away from this part of the talk. The first thing is that the gas phase N2O ratio in a disk is highly enhanced throughout most of the disk compared to the stellar value, and is more enhanced than the C2O ratio in gas, which tells us that we could potentially use both CO and N2O ratios to constrain the composition of disks and giant planet atmospheres. However, if we look at takeaway 8.3, we have also found that the locations of the CO and N2 snowlines are very, very uncertain and may span several tens of AU due to disk dynamics and ice morphology. So this tells us is that we really need observations if we really need to be able to better constrain the snowline locations as well as C2O and N2O ratios in disks and eventually planetary atmosphere compositions. And so I want to spend a few minutes just talking about some future directions. And so I put here again this cartoon of the disk showing chemical dynamical processes that occur in disks. And there are several of them which I plan to look at. So this is a table from one of my papers showing several of these processes and their effect on the snowline location. So at left arrows, the snowlines move inward. Right arrows, they move outward. Both arrows, you can go either way. So I've already looked at drift, gas accretion, particle composition. So from the dynamical point of view, the next thing that I want to look at is the turbulent diffusion. But so far in my thesis, I've only looked at this dynamics, and I've considered throughout that the chemistry is static. But chemical processes may also be important for the composition of disks and giant planets. And to illustrate that, I just want to show you this plot that shows different chemical and dynamical timescales in disks. So it's physics, chemistry, chemistry, physics, physics, chemistry. And the same color shows means that it's the same timescale. And you can see that some of the chemical timescales and some of the dynamical timescales are comparable, at least in some regions of the disk midplane. And so what this tells us is that we need to couple chemistry and dynamics if we want to obtain a more accurate picture of what is actually happening with the composition of disks and giant planets. And of course, coupling chemistry and dynamics is non-trivial, but this is something that I plan to do in the near future. So I'd like to end up with these 2 fundamental questions that I asked at the beginning of this thesis. And I think that my thesis has at least partially answered this question and has enhanced our understanding of planet formation as well as of the relation between disk and planet compositions. So thank you.
questions for Anna? Charles.
So I've got a question about the movement of the dust particles. When you're growing the atmosphere of a gas giant, is sedimentation of the dust particles out of the radiated portion of the atmosphere a significant contributor to the opacity?
Yes, I think so. So it is. But we are also considering the case where there's basically no more planetesimal accretion. So the contribution due to sedimentation is going to be pretty low, just because we have assumed that the core has basically accreted all the planetesimal that it could have. So there is still some settling from things that are still in the atmosphere, but otherwise it's not accumulating anything from outside.
So Anna, the second part where you talked about these dynamical viscous disk models.
Yep.
So you're using an alpha
Yep.
disk model. And these are very cold disks, so probably MRI doesn't work. That would be my guess. So my question is, what value of alpha did you use?
So yeah.
And how uncertain is that, and how would that feed into your uncertainty?
So I use an alpha of 0.01, which seems to be the standard that is used in disk, at least in disk models. It is very uncertain, as we know. So we have looked at alpha of 0.001, so factor of 10 smaller, and it did not change the results significantly, at least for this model. So a reduction of an order of magnitude, it really didn't change things much. But there's still a very large uncertainty in alpha. Like, that's just what it is.
I vaguely remember, at least in some of the older literature, people talked about 10 to the minus 2
Yeah.
for the more active parts of the disk. But for the colder parts, 10 to the minus 4 is a number I remember from some of the literature.
Okay. That's a good point. That's something that we can look at and just see if actually reducing it by 2 orders of magnitude would.
It would be better to go the other way, because I don't think theory can predict this alpha.
Yeah. No, that's yeah.
Oh, that is one generous comment.
You've shown that there's a large range based on your study of these ratios, the chemical ratios. So one could do that in 2 ways: a large uncertainty, and perhaps future work will narrow that range and show you where things really happen. But could it also be the case that the fact that you have a large range tells you that if conditions vary, perhaps due to minor changes in irradiation or something like that, that actually a wide range of values does occur, and that you will find diversity when you study planets in the real world?
So that's perfectly true. That's a very, very valid point. So this tells us there's a lot of diversity. But if we want to pin down, say, the composition of a specific giant planet forming at a certain location, then we need to be able to better constrain the snowline locations and the C2O or N2O ratios. But there's definitely going to be a large variety. And that's why for this we need more observations of more snowlines in different disks at different stages of their evolution. And that's just to start with.
So coming at this from the planet observation side, if you could measure a CO ratio or an N-to-O ratio of hot Jupiter, is that still a primordial atmosphere? Like, can you actually use that to say this planet formed here and migrated in, or does that migration and evolution just simply lose the initial conditions that it formed under?
I think so. You're saying if you say you find an ordered unity C2O ratio in a hot Jupiter, or just a superstellar?
Yeah, I guess the question I'm trying to ask is, at what point in the evolution of the planet can I look at its C2O ratio and say, okay, I know it formed here by this process? When you get upwelling in planetary atmospheres and they get bombarded, I guess, as they migrate in.
So I don't think in general you can actually tell. I think for this you actually need to also look at what happens with migration timescales and how these affect how the composition is going to change as the planet moves through the disk, since the disk composition is going to change. So I think it's probably a combination of what the final atmosphere of a planet is if it has migrated, is what it had accreted primordially, and then what it also accreted as it migrated. That's my guess.
Yes, about the first part. I understand that in your calculations you are fixing the core value, you're making it core mass fixed.
Yeah.
But I just want to ask for your opinion. So now there's this paradigm shift towards core growth, very efficient core growth by pebble accretion.
Yep.
So what would you expect is the effect of pebble accretion, how that would affect the rate that you acquire compared with planetesimal accretion?
So, so pebble accretion is expected to be really fast, so that would make things much easier, right? Because you just have, you had to have much more time to actually accumulate an atmosphere and form a gas giant. My understanding of pebble accretion is that also it assumes that basically it's focusing on the core formation. So I think that the model that we have in this vision that we first primarily form the core, then planetesimal accretion goes down, or pebble accretion is finished, and then you form the atmosphere. And so I think that, pebble accretion is actually one of the possible explanations in which we have found in which it would be possible to form these large cores, even at large separations. So that would something.
In terms of how that affects the critical format?
It's just going to lower it, I would think. I think it would just lower it.
Please.
So in looking at your N to O plot, the fact that the N to O ratio goes to infinity at the very end, it seems like that should be something that should be easy to see somehow. Is the place that we should be looking for this in cool, directly imaged planets, as we get more and more directly imaged planets and push down to temperatures where we could potentially see ammonia in their atmospheres? Would you expect to see some step function where all of a sudden oxygen disappears?
So it's not going to be a step function, of course, in reality, but I would expect that if we could actually look at this wide separation giant atmospheres and detect and some form constrain the N2O ratio, that's what I would expect. I would expect them to have it's a pretty narrow region between it may be a pretty narrow region between the CO and N2 snowline. So in this region, I would expect it to have a very enhanced nitrogen abundance.
Any additional questions for Anna? Then let's thank Anna again. Help yourself to some more breakfast, and we will retire to the private portion.
Yes. Fun. Okay.
That's great.
Oh, thank you. So may I just go to my office, just grab some things, and then come somewhere?
Ruth want to sit in for moral support.
Sorry?
No, Ruth wants to sit in for moral support and not ask any questions.
If the committee is okay, if she doesn't ask any questions.
Yeah, she just wanted to for moral support.
Okay, yeah.
Just want to double check.
Okay.
Hi, I'm Jenna.
Hi.
I don't know if we've met before.
I don't think so, yeah. I've seen you around a lot.
I really enjoyed your talk.
Thank you.
And so a lot of the stuff that I've been working on, I've been trying to measure these CO ratios, because the stuff I've been looking at the moment is these hot Jupiters, and I'm trying to figure out,
Right.
can I actually say anything about how